Hello, good afternoon. I'm feeling a little bit under the weather today, but hopefully it won't affect things too much. I don't want to have another one of those slightly chaotic afternoons. We'll see how we go anyway. My computer's also been feeling under the weather this afternoon, and hopefully that won't make things struggle too much either. We'll see how we go. I'm sure we'll be fine. Okay, so where are we? We have defined some differentially expressed genes. That's what we did yesterday. We spent our time yesterday afternoon talking about filters of various kinds. So we spoke about the filters which DSeq2 applies to our data, to do with the counts, so whether counts are for a gene are above 0 or above a certain low count thresholds, and also we talked about briefly about Cook's distance and the threshold that's applied to Cook's distance, and I showed you how to plot the counts for a gene using a built-in function of DSeq. And then we applied our own filters. So we wrote filters to remove genes which failed both a p-value, adjusted p-value threshold and a fold change threshold, because both statistical significance and effect size are important considerations when we're thinking about genes which are differentially expressed. And so that got us to the point yesterday, here we are, where we had applied these successive filters to our data frame. And what I did, rather than overwrite the data frame every time, I kept making new data frames. So every time I applied a new filter, I created a new data frame. And so we had got to the point by the end of yesterday's session where we had a data frame, this filter df3 data frame, which consists of just those genes which pass all of those filters. So all of the DSeq filters and both of our filters as well, our adjusted p-value less than 0.05 filter that we've applied here, and an absolute fold change greater than 1 filter that we've applied here. And so that brought us to the point at which we've got 141 genes in total which pass all of those filters that we've tried to or that we have applied, not tried to apply. So those we can consider at this point those to be our differentially expressed genes, and we want to learn more about those genes. So we want to learn more about what they are and what they do, both individually and in coordination. And so that's what we're going to do, not today, but probably we'll begin doing that process tomorrow, to have a think about what those genes are. So we need to identify them. So we need some annotation for those genes, but also think about what they do. So start to think about analysing them from a functional point of view, what their functions are in terms of the pathways that they belong to, or the biological processes that they take part in. And we'll start to think about that kind of functional, that pathway analysis later on this week. But today, what I want to look at is some very typical plots that we might want to create for our gene level differential expression analysis that we've done to this point. So we've looked at plotting generally, and I introduced you to ggplot2 a couple of weeks ago now, and we used ggplot2 to plot out some expression data from an example data set. We've also looked at some standard plots, which DSeq2 gives us access to. So DSeq2 has its plot PCA function, which actually uses ggplot2 to produce a principal components analysis plot, which we've done a few times now. And yesterday we met plot counts, which is another DSeq2 plotting function, which allowed us to produce a little scatter plot according to condition of the counts for a particular gene. Plot counts uses base graphics rather than ggplot2, so if we just remember what we did, let's pull that one back up because I've got it here. Plot counts, there it is. So this is a base graphics plot, so it doesn't look like a ggplot2 plot, and so this is giving us the counts, normalized counts for one particular gene, which is in the title of the plot, according to our experimental groups, our groups of interest, with a little bit of jitter. So they've separated out a little bit along the x-axis. So this is a relatively useful plot. It's a base plot. It's not a ggplot2 plot, but it works quite nicely, and it's convenient to use these plots that ggplot2 provides us with. The other one that we've seen is the dispersion estimates plot, which we talked about last week. So what I wanted to do today was certainly two plots and possibly a third, but we're definitely going to do two, and those two will be one from that DSeq2 provides us with, which is a method of visualizing all of the genes that we've tested for differential expression. And then I'm going to show you a second method for plotting a similar thing, but we're going to construct that plot ourselves. And then if we've got time, we will do a third thing as well, but we'll see how we go. I'm aware that time-wise, I quite often tend to... I'm not going to say prattle on. No, I am going to say prattle on. I tend to talk a lot. And so... that's why this forum is so ideal for me. And so I'm aware that we may not get through more than two visualizations. The first one, though, is quite simple. So the first visualization that we want to produce is what's called an MA plot. And DSeq2 gives us a function for producing an MA plot in much the same way as it gave us a function for producing a PCA plot and the other things that we've seen so far. So this is a built-in function of DSeq2, and it is plot MA, and it takes as an argument our results table as produced by DSeq. So that is the variable that results from this call to the results function. So that is our input for plot MA. So we're going to stick that in there. And that should be sufficient to produce a workable MA plot. There we go. So I'm going to zoom this in just to talk about this in a little bit more detail. So this is one of the reasons why I didn't just keep recycling the same the same variable name because I wanted to be able to use the DE-seq results table to produce this plot. So I wanted to keep it around. So let's zoom in on the plot and let's talk about it a little bit. This again is a base graphics plot. This isn't produced by ggplot2. So it is possible to fiddle with this, but I don't know how to do it as readily as I do, as readily as I know how to work with ggplot2 plots. But this is a very typical MA plot, and actually it probably doesn't need a great deal of configuration, to be honest. So the aim with plot MA is to produce this comparison of the mean normalized count, so that's effectively your base mean out of your results table, and fold change, which is what's shown on the y-axis. And so this illustrates a few things, actually. The first thing is the high level of variance that's present at low counts. So when you have low mean counts, you tend to have quite a substantial deviation from sort of zero fold change situation. So the genes with low count tend to have quite high fold changes, but they don't tend to be significantly differentially expressed. So the significant genes, according to the alpha that we gave to our call to results, which by default is 0.1, and we didn't change that. So anything that's coloured in red on here has an adjusted p-value lower than 0.1, which is not what we've then subsequently used to define our differentially expressed genes. So just so you're kind of aware of where we're at. So those genes with low expression, although they do tend to have to be more spread away from this zero line of no fold change, they don't tend to be significant, and that's because genes of low count don't tend to be robustly differentially expressed, and that's the noise that dominates, or the variance that dominates at this low count is technical variance, not biological variance, what they call shot noise. And so what we see here is kind of a lack of differentially expressed genes at this low count level. And then as the normalized count gets higher, so this is at 10 and then higher than that, you do tend to see differentially expressed genes creeping in. And obviously those differentially expressed genes tend to have a larger fold change. They tend to be away from this zero line, but not exclusively. And the higher your mean counts get, the more likely it is that genes will be differentially expressed. And also the further away you get from that zero line that runs across the middle, the more likely a gene is to be differentially expressed. And then we also have some limits on this plot. So they've limited the log fold change to 4, +4 or -4. And so genes which are beyond those extremes are indicated with these little arrows rather than points. This is quite a nice little plot for illustrating sort of trends in the data. This is a very typical MA plot. They tend to begin to look a bit like an X-wing from above in a lot of ways. They sort of taper out towards the right. They have these protrusions at the top and the bottom. So this is a very typical MA plot, and it's showing you nothing unusual about your data, which is good, and also that we do have differentially expressed genes, which is also good. So this is quite a nice visualization of the data, and this is the standard kind of visualization of all of these results that we get from DE-seq2. So that's the first of three. The second one that I wanted to produce is a so-called volcano plot, Joanna says the red points are the 141 differentially expressed genes. Yes, they are, but there are also other genes in there. So it's not just the 141 that we have said are differentially expressed. In here, there are also genes which would fail our log fold change threshold. So there are a bunch of genes in here which have a log fold change less than 1. So if we drew a line across at 1, you would see some genes fall closer to the 0 line than that. And that's because DSeq hasn't applied the same thresholds that we've applied. So the 141 are all in here, are all they are a part of that set of red points, but they're not all. That isn't all of them. There are more than that. Okay. So the second plot that I wanted to produce is another common visualization of all of the results, like all of these your tests for differential expression, and it's commonly called a volcano plot. And it's called a volcano plot because it looks like a volcano, or can look like a volcano in a typical analysis. So let's just have a quick talk about what is included on a volcano plot, and then we'll figure out how to produce that using ggplot. So let's go back to all of our panes, and also let me talk about what a volcano plot is. Okay, so let me just, I'm going to quickly draw on my whiteboard if I can get it working. So it's part of my computer being a bit of a pain today. Okay, it's loading. Also, by let's see if this is going to load. So I have got Jacob to draw a picture of the day today by popular demand. One of the things that came out in the comments on my survey was that people really like Jacob's picture of the day, so he's chuffed about that. So I've got to draw me one today. I'm just waiting for my whiteboard to load so that I can show you it in all of its magnificence. So that's just chugging away. The idea behind a volcano plot is what you're plotting out is in some ways is similar to an MA plot, but we're not going to plot the significance necessarily by the colours of the points, and we're going to include the p-value on the volcano plot as one of the axes. So I'm just trying to nudging my whiteboard along to try and get it up because I really want to show you Jacob's picture, and it's being a right pain. Let me just try. Let me try a couple of things. So I'm just going to put the cover image up and try to get this working in a better way. Bear with me. I knew this was going to happen today because of the way that things are. I just want whiteboard. Okay. No, I want to. For goodness sake. Sorry, everybody. I know that me swearing at my computer is not necessarily what you have logged on for today. But nevertheless, I will get there. Slowly but surely. My computer really doesn't want to play ball with me today for whatever reason. I suspect it's feeling as tired as I am. There we go. We're getting there. We're getting there. We're getting there. Maybe. Okay. Now it says almost ready. Now, as always, it says looks like it's taking longer than expected. Come on. Let's do this. I'll show you. There you go, to relieve your... There we are. Whee! Well, we got there eventually. Change of browser, and we got there eventually. So, there's Jacob's picture of the day. I got my... I think yesterday on Twitter, somebody posted, I think it's about the fourth or fifth picture that I've seen of cats watching me on YouTube, which is disconcerting. My own cat likes to run away from me, so it's interesting to see other cats paying attention to me. And so I talked about this with Jacob this morning, so he wanted to draw a cat, so consequently we have a cat saying meow. And because Disco Chick went down so well, we have a bit of a disco going on. Apparently it's tomato, not strawberry. So I don't know why, but who can reason with the mind of a 7-year-old? So there you go. That's Jacob's picture for today, which I'm going to try and make sure that he does them more regularly now. Okay, so volcano plots. I'm going to draw around Jacob's picture a little bit. I'm not going to delete it. So a volcano plot is a fairly straightforward thing. So on the x-axis, so the MA plot has log2 fold change on its y-axis, as we've already seen. The volcano plot has the log2 fold change on its x-axis. So you have this idea of how much a gene has changed on the x-axis. And then on the y-axis, we have an idea of how significant that change is. So on the y-axis, so clearly the x-axis is going to center around 0, and we're going to have upregulated genes and downregulated genes represented on it. And then on the y-axis of our volcano plot, we're going to have a representation of the adjusted p-value. But in order that more significant genes come up higher on our y-axis, we're going to log transform it. So actually the way that it's normally represented is as the minus log 10 of the p-value. And the reason for that is because p-values are between 1 and 0. If you, as we discussed yesterday, if you find the log of if you find the logarithm of a number between 1 and 0, sort of a decimal, then you get a negative number. So if you find the log to the base 10 of the p-value, then you've got a negative number, and so we just transform it into a positive number by finding the minus log, so that the more significant your p-value, so the smaller your p-value, the higher the minus log 10 p-value is. And what this means is when you produce a scatter plot from your data like this, so points with a low fold change tend to also have a small p-value. So they are present down near the origin, down near the middle of the fold change, and they have low p-value as well. So they're kind of down in this area at the bottom. And then as fold change increases, so the p-value also tends to increase. So you tend to get points and fewer of them that spread out like a fan from the middle. And so overall, the whole thing ends up looking a bit like a volcano, with this kind of, certainly the output from a volcano, shall we say, from just refreshing because it's not keeping up with me, where you've got kind of a little cloud of points down at the bottom, and then it kind of radiates out out from the center, and it does often end up looking like a volcano. There you go. That's my kind of rough representation of what a volcano plot ends up looking like. So that's what we want to draw. That's what we want to produce in R. In order to produce that, we want, for every gene that we have analysed, we want fold change and a p-value. And we have that data because we have it in our data frame that we one of the several data frames that we produced yesterday. We want it for every gene. So let me dispose of that. There we go. So if we think about all of our data frames that we had yesterday, so the first one was this result DF. That was all of the results from DSeq2. Now that has got quite a lot of rows where you have no adjusted p-value. It's also got quite a lot of rows where you have no fold change, because for things which have been filtered by DSeq, they're not present in that table. Those values are not present in that table. So we don't want those values. The one that's useful to us for this is this filter df1, because filter df1 contains all of the things that DSeq2 tested. So all 16,000 genes that were tested by DSeq, and they all have a log2 fold change, and they all have an adjusted p-value. So this is a data frame which is ready made for us to produce this visualization from. At the simplest level, the volcano plot, so we're going to use ggplot, ggplot2, but the function from ggplot2 that we're going to use is ggplot. So the data that we're going to use is filter df1, which is good to go. And at the simplest level, our aesthetics are that our x-axis is the log2 fold change. So that is a column in filter df1 that we already have available to ourselves. And then the y-axis is, so it's not the p-value. So the p-value is the p-adjust column, p-adj. That's the multiple testing corrected p-value. It's not that we want to plot. We want to plot the log 10 of that. So we transform it with log 10, but also that would be the log 10 would get more negative as our p-values got smaller, and we want it to get more positive, so we transform it. You can do it with an absolute, or you can just get the negative log 10. And so that's our aesthetics at the simplest level for our volcano plot. And then a volcano plot is a scatter plot. So we want to, the geometry that we want to plot is the point geometry, geom point. So that will draw a point for every row in our data set. And that is, at the simplest level, that is a volcano plot. It's not a very nice looking volcano plot, and this one doesn't look massively like a volcano, particularly because of this point all the way out here. It's got very, very high fold change, but not a huge p-value, so it kind of throws everything off. But that's a volcano plot. It's not very well styled, and we need to have a think about that a little bit. But it's a good starting point. Okay. That's the basics of a volcano plot, and it's quite a common visualization in these kind of differential expression experiments. This one's slightly thrown off because we have some extremes. We have some very low p-values, so that's giving us these genes up here which are skewing the whole plot by extending the p-value scale on the y-axis. We also have some very large fold changes as well. This will be a gene which will be 0 in one condition and have very high counts in the other condition, and so it has a very large fold change, and again is skewing our plot slightly. So what I would normally do with this, there's a few things I would normally do. The first thing would be that I would draw some lines on here for the thresholds that we've applied. So I'd put some vertical lines and a horizontal line on for the thresholds that we've applied. We can do that, but it's not going to be terribly useful. So the way that you add lines on to a ggplot is with the v-line and h-line geoms. So you've got geom v-line adds a vertical line to your plot, and you have to tell it the where you want to intercept the x-axis, so x-intercept. And our x-intercept is going to be 1 for this line. So that is our log2 fold change cutoff in the positive direction. We also want to add another one for our log2 fold change in the negative direction. That would have an x-intercept of -1. Okay, so this will draw two vertical lines on our plot. They're going to be relatively close together, and also drawing it in black is not particularly great. I'm going to improve the styling of this as we go. Okay, so that's our fold change cutoffs. So everything that lies to the left and right of those two lines hits our fold change cutoffs, so we consider to be differentially expressed by that threshold. But we also want a p-value threshold on, and so that's a horizontal line. So we have geom v line for a vertical line, we have geom h line for a horizontal line, and instead of having an x-intercept, that has a y-intercept. So the y-intercept would be, so the log 10 of 0.05 is not a particularly friendly number, so we're going to calculate it in here. So the minus log 10 of 0.05 is our p-value threshold represented on this plot. It's about 1.3, although not exactly. And so that will draw that threshold on as well. And so now everything in this quadrant, top left and top right, those are our 141 differentially expressed genes. But it would be nice to highlight those. So maybe we want to colour them in. And the way that I'm going to colour them in is I'm going to add a little bit of data into our data frame. So I'm going to add a conditional result into our data frame that gives us trues and falses for whether things pass our thresholds or not, which is best illustrated by example. So if you remember, we did these tests yesterday. So we've got this one here. We're working with df1 rather than df2 though. And we have this one here. These are our two tests. But we want to combine those tests. Okay, so this tells us all of the genes which have a p-value less than 0.05, and we can figure out how many of them there are by doing sum. Okay, so there are 325 genes with a p-value less than 0.05. This second filter tells us how many genes have an absolute fold change greater than 1. And again, we can use sum to tell us how many of those there are. There are 695 of those. But we're interested in not one set of those or the other set. We're interested in we're interested in the combination of those two. So we want to combine these two tests into one single test to say, or to give us all of the genes which have both a p-value less than 0.05 and a log2 fold change greater than 1 or less than -1. And we can do that by combine two relational statements using a special symbol. In this case, sorry, I've just done the wrong thing. We can combine them with an ampersand. So the ampersand here says, I want this to return true if both the left-hand side and the right-hand side are both true. So you're setting up a conditional sort of Boolean operation. So if this statement is true, and that's what the ampersand means, and this statement is true, then this will return true. Okay? So that's what the ampersand means here. It's joining these two relational statements together to say that I want both of these things to be true. If you want either of them to be true, so if you're interested in genes which have either a significant p-value or a large fold change, you can combine those two statements with the pipe, and that will tell you ones where either of those two conditions are true. But we want ones where both conditions are true, so we want to use the ampersand to say we want the p-value to be low and the fold change to be large. And that will give us, again, a logical vector of trues and falses, and we can use the sum function to find out how many of those are true. We already know the answer to that. It's 141. Those are our differentially expressed genes. Okay, but what I want to do, I don't want to use this to filter our data frame this time. What I want to do is I want to add this in as an additional column so that we can use it in ggplot. Okay, so I am going to save this as a column in filter df1. So filter df1 $test equals that. And so now if we look at filter df1, you'll see that we've added a 7th column, which is either true or false, depending on whether those conditions have been met. So we can sort by that and see the ones which are true. Here we are at the top. So you've got you've got a very small fold change and a p-value of 0.01. So that one is different. That one is significantly differentially expressed. Okay, so now we can use that column in our aesthetics. We're going to do it within the geom point, and we're going to say we want the color of our points to be dependent on our test column that we've just introduced. So if we rerun this now, we've added this test column into filter df1. This will add some color to our points, and some of them will be blue and some of them will be red, and that will be dependent on whether they pass our test conditions or not. So that's quite useful, quite handy. We can change the colors by doing scale, color, manual. It's values. I think it's values equals. If we do red and black, I need to add. There you go. Other way around. Black and red. There you go. So that allows you to colour the points in however you feel they should be coloured in. So you can change the colours according to your own whims. if you don't like the ggplot defaults, which quite often a lot of people don't. We're overplotting severely here, especially in the middle of this plot. So there's an awful lot of points in the middle here. And so what we're going to do is we're going to do a couple of things to relieve that to our geom point. So we're going to change the styling of all of our points. We're going to make them smaller, so by setting the size. And we're going to make them see-through by setting the alpha. So that where we've got overplotting, this should relieve it slightly, although there's going to be too much to really relieve it really well. So there you go. We've made the points a little bit smaller, and we've made them see-through, so that we get an idea of where there's lots and lots of overlapping points. A couple of other things. I don't like these heavy black lines. I think they would be better if they A, were a different colour, and B, were not just solid lines. And so we can change those as well. And it's just by adding things into the place where you plot them. So we can change the colour. What we're going to do, we'll just do green. If I had the time and the inclination, it might be nice to think about the colours a bit more detail than this. Let's colour in the horizontal line as well. Let's make that one blue. Okay, so that they're not quite so heavy and black. But also let's change the, and this is a really ugly plot, but let's also change the line type. I believe that you can do it like that. I think that works. Yes, there you go. So that's become a dashed line rather than a solid line. So line type 1 is the solid line, and then different numbers give you different types of lines. So 2 we saw was dashed, 3 therefore is dotted, and then you get dot dash as well, and various other line types. That's dashes and dots. So I think I quite like the dots for this. So let's add that into all of our others to stop them being quite such heavy lines. There we go. I have made an overwhelmingly ugly plot. Okay. I'm just going to, let's also add a theme, because I like theme BW. I don't like the grey background on the default, which we've discussed in the past. It would also be nice to do what the MA plot does and reduce the effect of these outliers somewhat. It is possible to do that, although it's quite difficult to do the transformation of the points outside of the scales into little arrows to make them change. Let me just it's X limit. Is X limbs? Yes, xlim, I think. So if you could do. So we're making this quite complicated now, but xlim. You do -3, then that will scale your x-axis. But if the points fall outside of the limits that you set, then they just aren't drawn. And you saw that then in this warning message. So it's removed 46 rows which don't fall within our x limits. So they're now just not drawn on the plot at all. which is not ideal. You could also do the same on the y, so y-lim 0, 10, just to limit on the y-axis as well. So now we're removing 78 things. It looks more like a volcano now, and it's a slightly neater plot. But you'd have to put quite a lot of work in to really be able to see those points that get removed. The legend, so Sarah's asking about the legend. That's part of the theme, so we can remove it in a theme. How do we hide the legend? You do it like this. So you add an additional, so after you've applied your theme, you add an additional theme to your plot, and you say legend position equals none, and that will make the legend disappear. Okay, you could move it around, you could remove the title, you can change the labels on it if you want. There's all sorts of things you can do within the theme to really style that legend how you want it to look. So you could, if you wanted to, you could put the legend on the top rather than down the side. So that makes the legend move rather than being on the right, it's now up at the top. So there are lots of ways of kind of styling these plots. Google really is your friend here. If you want to change the way a ggplot plot looks, that information is almost certainly out there already. Somebody else asked about putting gene names on the points. You can do that. Obviously, when you've got 15,000 genes like that, you would have to do it conditionally, so that only some of them have names on. Actually, the best way to take this plot and make it useful like that is to turn it into an interactive plot. So ggplot by default, just ggplot draws flat graphics. It just draws you a graphics object that you can't then interact with. But there's a relatively simple way to turn a flat ggplot plot into an interactive plot, and that's using a package in R called ggplotly, which I will just quickly do now because I hadn't really thought about doing this, but it's quite a good idea. We need to install a package. I'm just going to load Bioc Manager because I want the install function, and then we're going to do install, and the package that we want to install is called ggplotly with an ly on the end. So ggplotly. This package uses there's an online graphing tool called Plotly, which inherits a lot of the grammar of ggplot, and this package ggplotly allows you to trivially take a ggplot plot and render it using this Plotly library. So we're going to install that package. Like that. It'll just take a minute or two. I don't want to update any of my packages. Oh, ggplotly is not available for R363. That's odd. Have I spelt it wrong? What have I done wrong? Oh, it's just called, the package is just Plotly. Sorry, the package is called Plotly, not ggplotly. doing things from memory. So there you go, it's installing something this time. Okay, so that's installed the package Plotly, and that gives us the function ggplotly. So let's load the package. I'm going to do that up at the top, which I always do with package loading. Load the package up at the top of my script, and then down at the bottom, what we want to do is we want to save this plot. So we're going to save it as G, as a variable. I'm going to get rid of the X and Y limits for now, because I'm not sure they're helpful. And then to produce this plot as an interactive plot, we do ggplotly, and then the argument for that is the plot that we have produced. Okay, so if we run that and save our plot as a variable, and then we run ggplotly with that particular plot, then it opens a new pane here, which is called Viewer. So we're no longer in Plots, we're in Viewer. And Viewer, when it loads, is going to contain this is our volcano plot. But now we can interact with it, and we can hover over these points. And in theory, something should happen, and it doesn't look like it's going to. Yes, there you go. So you get a little, for every point, you get a little tooltip. You can add information into this tooltip by adding variables to your plot aesthetics. So we can add a variable into our plot aesthetic, which gives us the name of the particular of the gene, and that will carry over into our ggplotly plot. So let's just demonstrate how to do that with the ensemble gene IDs. So just remind myself of, it's slowed things down a little bit for me running this because it's an interactive plot with 15,000 points in. So it's a little bit, it's slightly got my already struggling computer today churning. Right, okay, so at present, let's zoom my console. Come on, RStudio, work with me here. There we go. So at present, the ensemble gene IDs in our data frame are not actually one of our variables. They're not a column in our data frame. We need to make them a column in our data frame in order to be able to use them, okay? Because otherwise ggplot doesn't know to look at the row names. It doesn't understand the row names because it's a tidyverse package, and the tidyverse doesn't like row names for whatever reason. So we need to convert our row names into a column. And luckily, the tidyverse gives us a nice convenient function for doing that called row names to column. Okay, so let's do that. I knew we wouldn't get time for the third visualization today. We might have to do that. Maybe we'll do that tomorrow. So let's add our ensemble gene IDs as a column. And to do that, we're going to do filter df1 equals row names to, is it as or to or as? Why can't I find this? It's in Tibble, I think. Maybe I haven't loaded Tibble. I haven't. Okay. Library Tibble. So it's a feature of the Tibble package. I should just load tidyverse. I like to be minimal about it, but it always comes back and bites me. Back down to the bottom. Come on. I'm going to have to close this. Just going to close the viewer item. if it lets me, because it's really slowing me down. There we go, that's better. Right, okay. So we've loaded the Tibble package, and now we should have row names to column, which is a function of Tibble. So that takes the argument, which is the data frame which has row names, which we want to convert to a column, and then the var argument is the name of that row name that you want to create. So I'm going to call it ens gene for ensemble gene ID. So that will add my row names in as a column rather than as row names themselves. So if we now have a look at filter df1, you should see that now, instead of having row names, we now have a column, which is ens gene. Okay, so then we add that in as an aesthetic. So we just call it something. We're not necessarily going to use it in our plotting, but we'll just add it in as a name. So that column becomes part of our aesthetic. Let's split that over multiple lines so everybody can see what I'm doing. There we go. And so now when we have a look at this interactive version of this volcano plot, which is going to appear here eventually, there we go, our little tooltips now should, because they contain the aesthetics that are attached to each point, it should contain the X position, the Y position, and the name. So there you go. The ensemble gene ID is now attached to that point. And when we've produced annotation, which I think we will do tomorrow, is we'll add the annotation on, and then we'll do the third visualization after we've done the annotation, so probably on Thursday. We can replace that ensemble gene ID for the gene symbol, so something that's slightly more human readable. And this then becomes quite a useful visualization of this. Yeah, unfortunately, with 16,000 data points, the interactive volcano plot gets a little bit cumbersome. But it is possible to, I think it's possible to zoom so you can interactively zoom the canvas here. So rather than having to set your limits, you can define them. There you go. I dragged a little box and it zoomed me in to a closer bit of the plot, and so the data I haven't removed any data this time in order to be able to zoom in to see a slightly more legible volcano plot than the kind of fully zoomed out version of all of the data. So yeah, Plotly and ggplotly particularly is quite a useful library. It's quite nice to be able to look at these interactive plots, even if it can be a little bit cumbersome with this many data points. Okay, so with that, I'm going to wrap up today. So tomorrow we will look at retrieving annotation for these ensemble gene IDs. That's the only thing that we've got to identify these genes at the moment is the ensemble gene ID. And we can use that to look up the annotation online. But actually, it makes a lot more sense to pull the annotation into our results in R. And so we'll look at how to do that tomorrow. And then we'll go from that, if we have time, we'll go from that to the third visualization, which I've alluded to but not really talked about in any detail yet, which is to produce a heat map from our differential express genes, because everybody loves a heat map. So we will endeavour to do that either tomorrow or, more realistically, Thursday. Okay, so that's me for today. Went into realms which I wasn't necessarily expecting with the interactive plot, but hopefully people have found that helpful and useful. And so, yes, I will see everybody tomorrow hopefully my computer will be feeling a little bit more healthy, and my headache will have gone. So yeah, look forward to seeing you then. So stay safe, keep well. See you tomorrow. Bye.